here are three different ways to look at simple harmonic motion. The easiest one is similar to the FET applet, where I displace this down and it goes upwards and downwards. And the acceleration is proportional to the displacement, but they occur in opposite directions. So we get A is equal to minus omega squared S. The second way is in terms of circular motion. So if I was to displace this down and leave it go, the motion of that is very similar to an object going around in a circle. In actual fact, if we had an object going around in a circle and if there was a flashlight on that side, the shadow of the object, the dot there, would move up and down like so. So the shadow of a particle moving with circular motion executes simple harmonic motion. So that's one way of looking at it. And what that means then is everything related to simple harmonic motion is also related to motion in a circle. So we can use some of the maths for circular motion and apply it to simple harmonic motion if required. Okay, let's have a look at the velocity. And we'll pause this in stages. So, at this stage in the equilibrium position, we can see that the velocity of the simple harmonic motion particle is a maximum, and the velocity of the equivalent circular motion particle is vertically downwards. And as we step through it, we'll see that this velocity here is a tangent to the circle, and if we were to resolve that into two components, one vertical and one horizontal, it's the vertical component that would be this thing here. So the velocity is at an angle there, meaning its vertical component is decreasing. As a result, the velocity here is decreasing. Watch what happens when we get to the bottom of the circle. I'm almost there, but look, at the bottom of the circle, the velocity is horizontal. It's got no vertical component. And for a simple harmonic motion object, we always look at the vertical component of the circularly moving object. So no velocity vertically in that case. And if that continues, then we see that when we get to the side, all vertical component here, maximum velocity there. Vertical component there is decreased, so the velocity of that's decreased, and when we get to the top, okay, vertical component is zero because it's moving horizontally only, so it's got no velocity at the extreme. And that's one way of looking at it. Okay, let's have a look at the acceleration then. It's very similar with the acceleration. For the object moving in a circular path, the acceleration, just like the centripetal force, is always directed towards the center of the circle. And the acceleration experienced by the object moving with simple harmonic motion is the vertical component of that. Right now the acceleration is horizontal, it's got no vertical component. Right now it's up at an angle, so it's got a horizontal and a vertical component. Its vertical component is that which is experienced by the object moving with simple harmonic motion. And then when it's at the bottom, all of its acceleration is directed up, and it's all vertical, and that's the acceleration experienced by the simple harmonic motion object. Now you may not get that in fifth year. You should have a better understanding of it the second time round or the third time round. You should have a better understanding of it in sixth year, certainly, when we redo vector components. But all I'm saying here, if you're in fifth year, is that there are velocities and accelerations as it moves around in a circular path, and the maths that we use to analyze and assess those can be used in the analysis and the assessment of a simple harmonic motion system. So if you took that point, that's probably most important. Let's go to the third way of looking at simple harmonic motion, and it's the graph method. So you will have seen this in maths already. The graph looks like that. Let's just look at one of them. That turns out to be a cosine graph. So if I pause it, what we're doing here is we're tracing out the path of the red dot up and down as time goes by. So think about this as if there was just a particle on the end of a spring and there was a pen underneath that, so a pen closer to the screen than that dot, and then underneath it was a piece of paper. So the piece of paper is there. And someone was pushing the piece of paper to the right. As that went up and down, what would end up happening is, and the paper moved, you'd get a wave like that, a sine wave or a cos wave, depending on where we start. Now you'll notice here that the amplitude of the wave, or the amplitude of the simple harmonic motion, is the height from there to there, which is the height from the equilibrium position to the extreme. So the amplitude is that, and for a wave the amplitude is that there, or that distance there. Now, if I could change the periodic time, this thing might go back and forward quicker, so that wave would be squished together if the period was larger, or it would be further apart if the periodic time was smaller. All right, let's get rid of that and let's have a look at the velocity. So I'm going now from a displacement time graph to a velocity time graph for simple harmonic motion. And you'll see there that it's almost the exact same. What we have is a sine or cos graph. But if I compare the two, and I'm really going above and beyond with this, when we compare the two, you see that one of them experiences a peak at a different time to the other. Right? And if I did the same then for displacement and acceleration, you'll see that one of them experiences a peak when the other one experiences a trough. So peaks and troughs. And hopefully this would make sense if you think about the formula acceleration is equal to minus omega squared s. The minus means that we flip the displacement, so we get the mirror image of it. It's a reflection in the x-axis. And then they're directly proportional as well, so that if I was to make the displacement larger, the acceleration would be larger, but not necessarily the same value. Right? So you can see there a particular value. If I reset it, we're looking at the graph, displacement and acceleration. And if I just move that down a small bit, so what we see there is A is proportional to minus S. In other words, big displacement, big acceleration, small displacement, small acceleration, and also the minus tells us that the acceleration and the displacement are in opposite directions, which is why the graphs are almost like a reflection of each other.